right, welcome back. So we have so far done chapter 3, where we developed the first derivative test for figuring out when we have a relative max or relative min. We've done the second derivative test, which uses the second derivative to figure out if we've got a relative max or a relative min. And I've reminded you of both of those tests here in the notes for 4.3. But we're actually just going to use the second derivative test in the things that we do today. So we're going to give a quick overview of the topic, which is optimization today. It's a really applied topic. I hope you'll find the problems interesting and sort of pay off in some ways for all of the hard work we've put into learning about derivatives and how to find derivatives and all of those rules and theorems that we have dealing with derivatives. So it's sort of all fair game now for optimization, but we're putting those rules, I hope you'll agree, to good use and figuring out actual applied problems. So we'll start with some that are maybe not something that you would do every day, but hopefully you can kind of see where these are headed, right, and what you might be able to do with derivatives in more complicated situations. So we'll do an overview of the topic, and then I'll go through 3 different examples, and hopefully that'll give us a good start on how to solve optimization problems. All right, so this first blank here is what I just said. We're going to do optimization problems. So one thing to keep in mind about optimization problems is that they can be, I think it's fair to say, a little challenging. And the reason is, well, there are a few, kind of all coming together at the same time. One is that these are word problems. And word problems typically are a bit more challenging than just sort of exercises because you have to read the problem really carefully, understand it, and then do some mathematics based on the information in the problem. So all of the optimization problems we do will be word problems in some way. Some will be easier to read than others, but we should kind of just be patient, right, with reading the problem, maybe more than once. You might read it out loud, but you really have to understand what the problem's asking to have any hope of making progress. Right? So we'll get some practice with that. But one thing to keep in mind also is that when possible, getting a picture or a diagram of the situation is going to be really helpful. So we won't necessarily get a picture for the first example we do, but we will for the others. All right, so while we can't memorize what to do for every optimization problem because they're almost all different, we can rely on the same process that we apply to all of the optimization problems. So we're going to outline the process and then we'll get some practice using it. All right, so our process, number 1 is to read the problem carefully. You may have to read it several times, and that's okay. But the main point you're trying to get out of that reading is to figure out what it is you're supposed to optimize. In other words, what's the quantity that is to be maximized or minimized? We've already done, like, graphically, I don't know if you'll remember these. We had graphs of sort of made-up profit functions, and we were looking for the maximum profit on the graph or the sort of minimum profit on the graph. So that's optimization, right? You're looking for either a maximum for some quantity of interest or a minimum for that quantity. So we're going to read the problem until we're very clear on what it is we're supposed to maximize or minimize. Next up, we're going to want a large picture or diagram, if appropriate. Now, I say large, not because that's any sort of technical requirement. It's just that one of the things that I observe often when students are first doing these sorts of problems is that the pictures are so tiny and cramped that you can't really make sense of them. It's hard to even see what's going on. So the sketch is only going to be helpful if it's big enough that you can actually visualize what's happening. So we're trying to figure out the equations that are going to be relevant. The equation to be optimized, that might be profit or area or volume. You'll see examples of all these things. But the equation that you're optimizing is called the fundamental equation. Or sometimes called the target equation. All right, so that's the thing we're most concerned with. But then there will be other information in the problem that relates the variables together. And these other equations are generally called constraints. Right, so we have the equation to be optimized. That's the fundamental or target equation. And then we have other equations, which are the constraints. And as we'll see, we use the constraints to put the target equation into a form that we can deal with using calculus. Right, so we'll kind of see what that means here in a little bit. All right, so this is usually one of the steps. We use the constraints. It's usually only one. So we use the constraint to get the target in terms of one variable. So often the target equation when we first start off is going to have more than one variable in it, typically two. And until you get to calculus 3, where we talk about multiple variables in optimization, until you get there, we really don't know what to do with two variables. And so we have to use the constraints to turn any of our functions or target equations into single variable equations. And then we can do derivatives on them. All right, so once we have the constraint as a single variable equation, then next we find the extreme values. All right, so this is where chapter 3 comes in, right? Finding the extreme values means we're going to take a derivative, set it equal to 0, find the places where it's 0 or doesn't exist, and then we will test those values to see if we get a max or a min. And then the test we use is actually going to be the second derivative test, just because it's typically easier than the first derivative. All right, and then the last thing is to give your solution in context. With correct units. So at the very end of an optimization problem, you shouldn't be left with a statement like x equals 2, right? It should be x equals 2 feet of fencing, or x equals 1,000 widgets should be produced, right? It's something that you have to tie back to the original context of the problem, okay? So that's our process. I'll leave this video then here, and I'll do sort of 3 separate videos, one for each of the examples, so you can sort of pick and choose which ones you want to see, and if you want to repeat one, it'll be a little bit easier that way. So I'll be back in just a second.